Doug, Stand-Up Physicist. This is the fourth of 6 shows devoted to my lectures at MIT during the independent activities period. Tonight's show is going to push an envelope because I barely understand what I'm talking about here. I think part of the reason is this is tough stuff, which means that people don't understand it so well. It may not be your problem, it may be the problem of the field itself. The topics tonight are quantization, which is how do you take a classical theory and turn it into one that quantum mechanics, the physics of small particles, can deal with, and the Standard Model, which explains all the subatomic particles seen in nature and 3 out of the 4 forces. It's a very successful theory, but it does not play nicely with gravity. And what I'm going to try and do is show maybe one way that it could work with gravity. I'm going to discuss quantizing a theory. First, we need to know the difference between classical physics and quantum mechanics. We then will go and calculate the momentum for the EM Lagrange density. We'll see a problem with that can be solved by fixing the gauge. We calculate the momentum for EM with the gauge fixed. We interpret the results of that quantization process, but there are still some problems. So I go ahead and calculate the momentum for the GEM Lagrange density, interpret that, and then have hope that it will do a very good job for explaining gravity and electromagnetism even in the quantum mechanical domain. What is the difference between classical and quantum mechanics? In classical physics, observables can be measured by numbers. And if you form the commutator of any 2 observables, like potential and momentum, and then subtract momentum times potential, it comes out to 0. There's no surprise there at all. What is surprising is what happens with quantum mechanics. Observables now are operators. They are not numbers. Those operators act on a complex valued wave function. What can be observed is the norm of that wave function. Most observables are independent of each other. However, there are pairs of conjugate observables where if you take the momentum in the x direction and the potential in the x direction, act on that on the wave function phi, and subtract from it the opposite, then you do not end up with 0. This has to be the case if you want to quantize your theory. If there is a 0 in there, then with a conjugate pair of operators, then the theory cannot be quantized. Let us calculate the momentum of the EM Lagrange density. First, write out the Lagrange density without any indices. Write out each and every component. It takes a few lines, but it's worth it. Because the next step is to take the derivative of that Lagrange density with respect to the time derivative of the potential. So that would be d phi dt, dAx dt, day dt, and dAz dt. Do that with this Lagrange density, and the first component of the 4 potential is 0. So, with its conjugate pair, which would be the potential times the potential phi, times 0 minus 0 times the potential is 0. Therefore, this Lagrange density cannot be quantized. So what do physicists do? They fix the gauge. So what is a gauge? Well, the way I think about it is to think about the antisymmetric field strength tensor and how it has zeros down the diagonal. It has zeros down the diagonal because anything living there gets subtracted away when you make the tensor antisymmetric. So what we do here is that we can choose whatever we want to fill in that diagonal. One of the choices in gauge is called the Coulomb gauge, where the divergence of A is 0. Another choice is the Lorentz gauge, where the time derivative of phi plus the divergence of A equals 0. It's in fact this gauge we will use to quantize the electromagnetic Lagrange density. So now we want to calculate the momentum of the EM Lagrange density in the Lorentz gauge. The process is the same. We write out all the components, and you can see there are even more than before. We take exactly the same kind of derivative. And because of those extra terms, that first component of the 4 momentum is not 0. So the theory can be quantized. Now let's interpret the quantization. There are 4 modes of emission. 2 modes are transverse. So if it's moving along this way, that's the transverse modes. One of the modes is longitudinal, and another mode is scalar. The transverse modes do the work of EM. The longitudinal modes and the scalar mode in particular are problems. The scalar mode is a problem because it can be either positive or negative. So it could lead to positive electric charges with the same signs either attracting or repelling. But that's not the way electrical charges have ever been observed to behave that have the same charge. All of them repel. For this reason, we must make sure that the scalar mode of emission cannot happen. So what we do is we add this supplementary condition. And the supplementary condition ensures that those modes are always virtual. Here's my skeptical analysis of fixing the Lorentz gauge. Photons must transform like vectors. A scalar photon does not transform like a vector. Therefore, it's an oxymoron. And eliminating an oxymoron using the supplementary condition is just not satisfying. We have to struggle to find a new interpretation of a 4-dimensional wave equation. Now we will go and calculate the momentum of the GEM Lagrange density. We will do it as we have done it the last 2 times. First, write out the GEM Lagrange density in all of its terms. You'll notice there are fewer of them. I think the theory is more elegant and compact. Take the same derivative as before, and you end up with a 4 momentum where none of the terms are 0, and so it means that it could be quantized. Let's interpret this quantization approach. There are going to be, as before, 4 modes of emission. There will be 2 transverse modes, a longitudinal mode, and a scalar mode. The 2 transverse modes represent EM. It is a spin 1 field because, like electric charges, repel. The scalar and longitudinal modes are representing gravity, the graviton. It travels at the speed of light, like charges attract. And because of this, it's not going to run into the same technical problem that faced the entire spin 1 field of a 4D wave equation. By making the 4D wave equation represent 2 types of spin fields, we get around that technical problem. But it also makes a testable prediction. Gravity waves, according to general relativity, are transverse modes of emission. And for that reason, if we go and detect a gravitational wave, general relativity predicts that the modes of emission should be transverse. My GEM unification theory predicts that that will not be the case. That if we do calculate the mode of transmission, it will not be transverse. Just to be very clear, if we detect gravitational waves, which is really beyond our means right now, but we have several experiments trying, and we figure out how the mode of transmission, if it is transverse, then my theory is wrong. I'm not going to dodge anything here, but if the newspapers come back and they say, oh my goodness, something's wrong with general relativity, you will know that there's something right with this GEM unification. The standard model of particle physics does a great job at explaining most of the forces of nature, but not gravity. Hopefully we'll see a way where gravity could live in peace with the standard model. We start with group theory because that underlies the standard model. We will show you some examples of group theory relevant to the standard model. We'll write out exactly what the standard model is and write out the Lagrange density. And then I will look at how multiplication needs to work with 4 complex valued 4 potentials that may give us a clue as to where gravity lives with the standard model. Group theory is the way that mathematicians systematically organize symmetry. You start with a set that has lots of individual components, and you have a binary operator, call it either plus or multiplication, and it has the property that if you take any 2 elements and act on it with that operator, the result will always be in that set. A group must have an identity element. It must have inverses for everyone, and it must be associative. The 2 simplest examples are the real numbers and the binary operation plus. The identity operator is 0. 5 plus 0 is 5. The inverse of 5 is minus 5. 5 minus 5 is 0, the identity operator. Another example is the real numbers without 0 and multiplication. This time the identity operator is 1. 5 times 1 is 5. The inverse of 5 is a fifth, and 5 times a fifth is 1, the identity operator. But now let's look at groups that are involved in the standard model. The first one is U1. This is complex numbers that have a norm of 1. Complex numbers are actually pairs of numbers that kind of behave together as a number. So you can add them, subtract them, multiply, and divide them. The identity element is 1. The inverse is the conjugate of a complex number. The way I visualize this is I think of a unit circle. All the elements of U1 live on that circle. The conjugates live on the other side of that circle. And you can represent this group using exponentials, the one that I've written out there. And in this case, you only need one number in that exponential. This is important for an area of math known as Lie algebras. The fact that there's one element to that Lie algebra is very important to actual physical considerations. SU2 symmetry is for the quaternions that have a unit norm. A quaternion is like a complex number, but instead of a pair of numbers, it's got 4 numbers. The unit is again 1. The inverse is again the conjugate. And this time we have a unit sphere, where if you go to the opposite side of the sphere, then you have the inverse. If you write this as an exponential, it will require 3 numbers in that exponential, or 3 numbers in your Lie algebra to characterize any unit quaternion. The standard model is the way to characterize the organization of subatomic particles in nature. It describes 3 out of the 4 forces of nature. U1 symmetry applies to light, EM. Its Lie algebra only has 1 degree of freedom, and there is only one particle that does EM forces, the photon. SU2 symmetry is associated with the weak force. This is the stuff of radiation. There are 3 particles associated with SU2 because there are 3 degrees of freedom in its Lie algebra. It's the W plus, the W minus, and the Z. And finally, there's SU2 symmetry, which is about the strong force, which is about how nuclei kind of interact with each other. These are the gluons. What is missing is gravity. There is no place in this theory at this time for gravity. As a matter of fact, the theory works when everything has 0 mass. And one must use something called the Higgs mechanism to give things mass. But we have yet to detect the Higgs particle. We are spending several $billion to detect the Higgs particle, because it is that important to the standard model and how we currently understand physics. Now we are in a position to write out the standard model Grunge density. This will describe all the energy interactions that involve light, the weak force, and the strong force. It's rather simple, but deceptive, because there are only 4 symbols there. There's 2 wave functions, a spinor matrix, and a covariant derivative. But let's look a little further. Well, actually, I'm not going to go into this spinor matrix. It's too confusing. I don't even get it. But the covariant derivative can be broken into smaller parts. There's the normal derivative, and then there is a term for electromagnetism. It has a coupling constant, Y, to generate a U1 symmetry, and a 4 potential, A. For the weak force, there is again a coupling constant, a different one, and there is a generator of symmetry, tau, and there is the 4 potential, W, which also has 3 internal symmetries. Then the final term is for the strong force. Again, a coupling term, a symmetry generation term, lambda, and finally G, the 4 potential, which has 8 internal bits of symmetry. I represent that schematically as a few dots for EM, a few more dots for the weak force, and a lot more dots to deal with the nuclear forces. Do I completely understand this? Absolutely not. But at least I have more of a technical handle on what's going on. The standard model depends on group theory. And group theory has as part of its definition a binary operator we call multiplication. So let's be careful about how to define multiplication in this context. Because what we want to do is start with 2 complex valued 4 vectors, 4 potentials, and end up with a real number. I think that's going to require 4 things. First of all, we're going to have to take conjugates so that the complex values can turn out to be real when you contract them with their counterpart. Then you need to use a parity operator, which switches the sign of the 3 vector in order for all the signs to work out positive. You are going to need a metric tensor because you have 2 4 vectors and you want to end up with a scalar. And finally, I think that all 4 potentials are going to have to be normalized to themselves because that type of symmetry appears in the standard model. So now, if I were to square a 4 potential with itself, what I would do is I would take that potential, divide it by its norm, and then contract that with another 4 potential where I had taken the conjugates and acted on it with the parity operator and contracted that using a metric tensor. So if we think about this in space-time, in flat spacetime, that will simply add up to 1 every time. But in curved spacetime, the coefficients of the metric will be different from 1. What this does in essence is breaks U1 symmetry, breaks SU2 symmetry, breaks SU3 symmetry, but in really a rather polite way. The polite way is because the circles and the spheres simply get a little larger. Nothing is changed about the Lie algebra, which has to do with how many particles are involved in the forces. It's just that the size of the circle gets bigger. Now, what determines the size of that circle? That would be mass charge. And so we have a systematic way to incorporate a changing metric in the standard model without destroying the fundamental symmetries. This may in fact end up eliminating the entire need for the Higgs particle. The Higgs particle is also very polite in how it deals with U1, SU2, and SU3 symmetry. but it is in no way related to gravity. Here, by being careful how we define multiplication, we can see the metric is already there. And simply by changing the size of the circles and the spheres, we may be able to incorporate gravity with the standard model. Thank you very much.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting, full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the grade he gave her was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof, rock star.
Oh, hi. I don't really know how to play guitar, but I really like the look. I mean, it's so cool. I kind of feel that way about like my physics. Like the equations are like so cool, but I am so not a pro physics guy. See, a pro guitarist, you know, you kind of like, you know, all up here and stuff, but it's kind of clear. I don't know what I'm doing. And so I'm kind of waiting for my Jimi Hendrix of physics to show up and take my guitar and like really go with it.